Good morning, everyone. This is our first class of the biological principles in environmental engineering. And today we are talking about the concept of the most important things for engineering designs of a biological systems that's coming from the mass balance concept we call stoichiometry and energetics. And about the mass balance is coming from the concept here we are listing about the chemical reactions we are going to be balancing, and the chemical reactions involved in those like energy and also the nutrients and also something like a vitamin trace elements that is used for microorganisms for growth. So it's including the biomass synthesis and also the energy productions during their metabolisms. And for examples, here we are talking about one kind of the bacteria that we call aerobics. It requires like energy coming from the oxygens as an electron receptor, and also coming from organic carbons as their electron donors, and combine together to get some energy production, and also like nitrogen and phosphates as their nutrients for biomass growth. So by understanding the mass balancing between the chemical reactions for microorganism synthesis, we can understanding those kind of the chemical reactions and also their byproducts and biomass generation to understanding the amount of the cells they can produce during their metabolisms. So about the how to balance in the chemical equations, we hold the concept of stoichiometry here. And so this concept is coming to balancing the molar ratio among the reactants and also the products. Okay, so the chemical equation is combining from uh, one kind of the electron donor and another part is the electron acceptor, and also coming to synthesize the cell itself. So they will have like the partition of the electrons to one part to the cell synthesis, and another part is going to maintaining the cellular activity. So for example, as we can see here for the equation 5.1 here, they are very simple and basic balancing chemical reactions between the one kind of the protein casein that is coming from one digested uh, protein substance, and also balancing together for the bacterial cells synthesis here. So from this equation, we can understand in like 1 molar of the casein chemicals that requires for aerobics to oxidation, they require like 3 more of oxygens here, and after the oxidation, they will generate like 1 molar of the bacterial cell and produce like 1 molar of the ammonia, bicarbonate, and also the carbon dioxide. So which means this oxidation reactions is like the respiration reactions here. Okay, so within those chemical reactions, we will involve several concepts between the within the chemical reactions. First, the microbial reactions generally involves like oxidation and reduction reactions together. So this is our first concept. And to combine those oxidation and the reduction reactions, they can generate like electron transfer chains to harvest those electrons and also store those electrons within their electron carriers, and to generate like uh, intercellular energy, or use those energy to synthesize their cell. So second concept within the chemical uh, reactions with the microorganisms like the cells, they are have two roles. One is as a catalyst to uh, trigger those chemical reactions, and another role is about they are also the products of the reaction. So when you harvest those energies, you will get more and more cells within the like bioreactor or the systems, and so you will get more like active cells from those electron transfer chain or electron transfer chemical reactions. So this is basically the concept of a stoichiometry chemical reactions. So like in our previous examples, we use casein as our like substrates and also use them for aerobic oxidation for cell growth. And so within these reactions, if you coming from 1,000 kilogram per day of casein used for bacteria, basically you can calculate those products or like the requirement of the oxygens from the chemical reactions. For example, you will get like about uh like for example like a per 184 gram of the casein consumed, you will require like a 96 gram of oxygens to be supplied and also generate for about 113 gram of new microbial cells. So if you consume like a thousand kilogram per day of casein, you need to supply like a 520 kilogram per day of the oxygens via aeration, and also to generate like 610 kilogram per day of a biomass that is coming as like maybe activated sludge, and you will have to facing those activated sludge that will need to be treated after uh, they are getting inner and inner in within your biosystems. So from the examples here, we're understanding that we will require like several items within the chemical reactions. The first one is you will need one like empirical formula for the cells, and this is basically like a very general concept here. So one chemical formula that represents for the bacterial cells, and also another part is you will need like a framework that is describing the electron donor substrates. So for the example, that is casein, and so that will use for like generate or providing electrons to all the chemical all the reactions they require, like for oxidation and reduction reactions. And the third part is you will have to understanding the proportions about the how much amount of the electrons that is used for synthesis new biomass, and also how much amount of the electron donor, no, electrons coming from the electron donor that is used for balancing the energy. Okay, so we will introduce how to understanding or calculate those proportions afterward. So about the empirical formula for microbial cells, we can move a little bit forward here. So we can understand in that here is like a very general formula that's used to describing the bacterial cells we call C5H7O2N. So this is generally used for cell, sorry, for bacterial cells, very like a high molecular weights molecules like carbohydrates, proteins, and also fats. And so combine them together and have like a empirical formula that describing the bacterial cells. So sometimes the bacterial cells not only including those four like elements. For example, we know the bacteria that's require like phosphorus within their cells. but they are generally like has very little amount of the phosphorus within their cells. So the sometimes the uh, empirical formula won't describe the portion of the phosphorus that's within their uh, chemical formula. And so we can understand more about the empirical formula for bacterial cells from the section 5.2 here. Here we have like several tables. We can move to the next page, and we have like uh, another page here. So we can see the table 5.1 and also the table 5.2 here to understanding those like chemical composition for the major organic chemicals within the cells like proteins and carbohydrates, lipids, DNA, RNA, something like that. And so you will see like because they have like a different percentage within the cell dry weight, so we will merge those numbers together. And so generally you will have like more in more detail. You can see the table 5.1. So the first one is the most simplest and also the most general used empirical formula for a bacterial cell. However, if you have another conditions like if you treat or you feed the bacteria with different kind of the uh, organo organo organic substance like acetate or like glycine, you will have like change their chemical compositions of the cells. So here you will have like a different empirical formula, but generally we will use the C5H7O2N as the most easiest way to describe the bacterial cells. Part of we will skip this for the formulation for cells containing storage products. That is like the extra information to describe or to uh, presenting the chemical composition of the cell formula. So we will skip this one, and then we will jump into the section 5.4 to understanding the partitioning of the electron harvest from the electron donors. Okay, so first things we will see here is if the microorganisms use electron donor substrates, so generally they will separate the electrons they used. For one part is for the cell synthesis, and another portion is used for the providing any energy that's required for the cell to maintain itself. So about the portions that you use for the cell synthesis, we will use like uh, Fs0 as the portion part, and also for the electron that we use to maintaining the energy or maintain the cell metabolisms, we will use Fe0 as the portion number. So basically, their assumption would be like equal to one because you're coming from like a one electron oxidation reduction chemical reaction. So we can see the figures 5.1 here. So basically, you harvest all the electron from your electron donor substrates, and the electron coming from the substrates will divide into two portions. One is for the energy production, So here we call the Fe0. So another part is used for cell synthesis. So we use Fs0 as its symbols. And so those two kinds combined will equal to 1. So that will means you don't have any other like electrons coming to the other part of the additional reactions. And for the cell synthesis, all you can get is first of all is the active bacterial cells, and those activated cells will finally uh, become like an inner cell here. So they will starting to decompose and also to get decayed. And during the cell decays, they also generate some like residue energies. So part of the activated bacterial cells, they will generate a little bit amount of the energy used for maintaining or some kind of reaction end products that is used for maybe we use for another bacterial cell growth. And additional parts will be get like a cell residue that is called inner cells that is have no purpose for the following used. So they will get like a all the inner part of the biomass. So the portion of the for the cell synthesis, the Fs0 can be converted into another concept that is used for like uh, the we call the biomass yield. So the biomass yield is basically the concept of the how much COD consumed that will generate how much amount of the biomass. So here we can like uh, go back to the page here. Okay, so for the equation 5.2, we can understand it if you would like to uh, manipulate like a chemical reactions that's used for like calculate how much amount of the oxygens you required for like oxidize one organic chemicals. We can apply this part of the equations to calculate their like balancing numbers between the organic chemicals and also the oxygen uh, molar ratio. So if we use like C5H7O2 and here, so basically we will need like uh, divided by 2 and 2 times 5 plus 0.5 times 7 minus 2 minus 1.5 times 1 here. So basically it's like a 5 more molar of actions you will require to like consuming or like to uh, convert completely convert the uh, biomass to COD. So here we are understanding that to convert the cell yield, or we call biomass yield, we're coming from the how much amount of COD we need to get into like how much grain of the cell we produced. So for here, the part here, so the Ne represents the number of the electron equivalents in the empirical mole of cells, and also coming to convert from the oxygens here. So which means here we need like 5 molar of oxygens, and you stay the A number of A here represents uh, the equivalent weight of the oxygens. So by converting one molecule of the oxygens, we will require like 4 electrons. So basically, how much amount of the equivalent weight we can calculate is 32 is the molecular weight of the oxygens and divided by the 4 electrons. So which means 8 grams as their equivalent weight. So we times 5 here and use 5 molar. So here we know we will require like the 20 electron per molar cells. And so the MC represents to the molecular weight of the biomass. Here we say, so it's 113 grams. So we divided the 130 to like 20, 8 times 20 here. So we will get like okay. So the Ne is equals to the 5 mole of oxygen consumed, and per mole of oxygen consumed would require like 4 electron converted. So it's times 4 equals 20. So our Ne equals to 20 like electron equivalent per molar cells. Okay, so the MC here is the molecular weight of the cells, bacterial cells. So we're coming from the C5H7O2N. So the molecular weight would be like 113 here. So the overall calculations here, we will know for the true yield of the biomass, we will know that it was the like the how much amount of the electron portions times the molecular weight of the microbial cell divided by A times 20. So that will around equals to about 0.706 times the FS0. So the true yield, generally we will use the true yield, these numbers used for describing how much amount of the microbial cell that will grows within the biosystems, and we can calculate their growth rates directly from using the differential equations. This divided the time differential of the times and also the biomass here. So that will generate equals to the true yield times the how much amount of the substrates they are using, because the substrates we can understanding is how much time of the COD they consumed, and if we times how much COD they will convert to the biomass here, and we can understanding how much time they will generate their biomass. And for the later part here, the B representing to the decay rates. So basically we have to minus the decay portion of the biomass. So one part is you generate new biomass, and another part is your active cells will get decayed, and they will finally diminish from the bioreactors. So you have to minus this portion. So this is all for decay. So you will get a final true yield of the microorganisms in the biosystems. Okay, so basically you can get those like a true yield, or you can get how much amount of the cell that's growing within your bacteria uh, based on the stoichiometry reaction balancing. Okay, for our next part, we are coming to discuss the overall reactions for biological growth here. So we move to Okay, we move to the next page here. Okay, so for the section 5.5 here, okay, so as we just mentioned about the bacterial growth involve two core reactions. So one is for the energy production and another one is for cellular synthesis. And the energy production also coming from two core reactions. One is for oxidation, half reaction, and another one is reduction, half reaction. Okay, so including those two uh, core reactions, you will get like three reactions: one oxidation, and two reduction, and three cellular synthesis. Okay, so you will need to learn how to combine those three reactions to get into the one stoichiometric reactions uh, simultaneously for biological growth and also for substrate utilization. Okay, so we will move to the next page here, and you will see lots of the half reactions. They are listed in like table 5.3 and also 5.4. Let me just cover the next page. Table 5.3 includes many common electron acceptor half reactions and also the cell synthesis half reactions. You will have to look at here. You will get one part of the common electron acceptor half reactions that is used for like oxygen, ferric ion, and also nitrate and sulfate as their electron acceptor, uh, the ions. And also sometimes you will have to use like a CO2 as their for autotrophic growth electron acceptors. And for those half reactions for cell synthesis, sometimes you will use different uh, nitrogen sources, including ammonia, nitrate, nitrite, and also sometimes you will have to fix nitrogens from the atmospheric air. So this is N2. So basically they are all cell synthesis half reactions. You will see here your final products are all C5H7O2N, that is bacterial cells. But if you are using different ammonia, different nitrogen sources, you will get like different balancing molar ratio for the how much amount of the bacterial cells you are producing. And if you turn to the next page for the table 5.4 and also the next page, this is continuous table, and the table 5.5, you will have more half reactions using for like those electron donors. This is for electron donors. So sometimes the electron donors are generally use the organic chemicals for providing electrons. So you can see here like acetate, benzene, benzoate, okay, like citrate. That's a very common used organic chemicals can produce electrons. And if you need more like the other type of the organics, here has lots of the half reactions. And for the table 5.5, that's inorganic half reactions, and generally they are using for electron acceptor. Okay, so sometimes they are combining like two inorganic substance, like for instance from ammonia to nitrate, or convert ammonia to nitrite, electric. So there's generally lots of the inorganic, like sometimes you can use hydrogen, and also sometimes you will use like sulfate to sulfide. So that's we call the sulfate reducing bacteria. Okay, so they are listing many reactions, including their free energy here, and also their half reactions here. So half reactions, we are talking about the one electron conversion reactions. So within the one electron half reactions, you can list all three chemical reactions, including oxidation and also the reduction and also the cell synthesis. Combine them together and you can merge them into one reactions, because all they need is one electron convert conversion. Okay, so we can move back to the content of how to balancing those chemical reactions. Okay, if we, so right now we are moving to page 155. Okay, here. So we begin from the reactions we think for the energy, sorry, for the energy reactions. So energy coming from, as we say, the oxidation and the reduction chemical reactions. So when we are combining those half reactions together from the tables, we will use the Re as the energy reactions, and coming from one oxidation reactions, and also another. So this is the oxidation reactions, and also acceptors, electron acceptor reactions is used for reduction reactions. So we combine these together to get the energy reactions. And for the cell synthesis reactions, those cell that synthesize, we have the cell synthesis half reactions, and also they are coming from the electron donor. So this is also the oxidation, as we just say the casein converts into the biomass. So we will have these two core reactions. Okay, so about the combining them together, we will need to like list them together as we see here. So we will get like a Ra is for electron receptor, and minus the Rd electron donor. So this part is used for energy production. Okay. So similarly, you will have to combine the Rc that's for cell synthesis, and also minus the Rd that is used for coming from the electron donor. So if you select like acetate as your substrate, okay. So first, since you will need to come in from maybe choosing the right uh, electron acceptor. So here they are selecting using the nitrate as their electron acceptor, and convert them into the nitrogen gas, and use acetate as their electron donor. So they convert. So all you need to list is one electron reaction here. So basically the first RA, the equation 5.11 is coming from the, here we saw the electron acceptors here. So this coming from the I7 reactions. This come the nitrate to the nitrogen gas here. So you just put this equation. And another one is coming from the acetate. So that's basically the first. Okay. So here you will get the nitrate. Basically just move them to the reactant, and also the organic substrate. Also move them to the reactant. And so the overall things you will move to like the product here. So balancing the like the proton together, and also the other part of like the CO2, bicarbonate, and the H2O. You have to combine these two things together, so you will get the final uh, energy production chemical reaction. So as the same things, you choose the cell synthesis reactions coming from synthesized from the ammonia as the nitrogen sources. So you will also get additional like RS chemical reactions together. So that's coming from like organics and to synthesis cells. So by combining the RE and the RS, as we know previously, we can times the Fe and also the Fs together with those chemical reactions, and we know uh, these two combination would be like equal to 1. So basically here, if we put the Fe and Re together, and also the FSRS together, so the overall reactions here will be like a 0.33 the benzoate, and convert to like a 0.02 molar of the biomass, and produce like 0.06 nitrogen gases. Here we forgot to tell you guys about the assumption for Fe and also for the Fs. So we move to our previous pages. Here, I just assumed if the Fs will be 0.4 and the Fe will be 0.6 for the benzoate electron equivalent reactions. So we can just put the Fs0 here as 0.4. So here will be 0.6, and to get the final overall reactions. So we move to the next page here. So what we saw just previously is how we can combine those three core reactions. One is oxidation, and another one is reduction. Those two have reactions to combine them together to get here the Re seems times Fe, and here we also combine another two core reactions that is coming from cell synthesis, and also the electron donor, that is the Ras and times the Fas here. So if we get those equations by combining them here, so we can become Fe times Ra minus the Fe times Rd, and also plus the Fs times Rc minus the Fs times Rd. So we can combine them together as the FERA plus the FSRC minus the FE plus FSRD. And as we know that the Fe plus Fs equals to 1, so this equation will become the FERA plus FSRC minus RD. So that's coming from as the equation 5.20 here. So it's like a simplified overall reactions expression. So we just times the Ra with our Fe ratio and also plus the Rc with our Fs ratio and minus the overall the electron donor reaction. Okay, so within those with the equation 5.20, we can use them to very easily calculate the overall reactions. As an example here, they are using like uh, oxidized nitrogen sources and also use the benzoate as their electron donor. So again, their assumptions for the Fe is 0.64, 0.65, and the Fs then will be like 0.35. Okay, so they can very easily put the equation together. So the Fe will be 0.65 times Ra. So the Ra coming from, okay, the I7 table 5.3. So the table 5.3, as we just saw, the R7 here is, okay, 1/5. So as you just calculate the 1/5, 0.65 times the 1/5, that is will be just equal to 0.65 divided by 5 equals 0.13. So that's exactly the same things as we wrote down here, 0.13 of the nitrate. Okay, so you will get like 0.65 electrons here, and plus the Fs will be 0.35, so you'll get 0.35 electron here, and to minus the RD, so the RD will be like the full half fractions. You don't have to times any like fractions here, so we'll get like a whole electrons converted. So basically here you combine them together equals to 1, so you will get like finally the overall reaction balanced with their electrons. Okay, so this will be the final overall reactions. Okay, so I will recommend you guys to doing the example 5.3 as your homework. So you can just looking into if the assumption Fe is 0.9, and which means the Fs equals 0.1, and if you want to understanding the nitrification, also we haven't teach you what's the nitrification reactions. So basically, they are using the first things is oxygen as their electron acceptor, and the RC is using ammonia as their nitrogen sources for cell synthesis, and the RD electron donor is coming from the ammonia. So nitrification is used ammonia as electron donor and the oxygen as the electron acceptor in to get energy. So sometimes you will have to use CO2 as your carbon sources. Okay, so you can try to balancing the overall chemical reactions here. Just try by yourself at home. So here our Fe will be 0.9, our Fs will be 0.1. So you can put those chemical reactions together. Also, so after you get the overall reactions here, you can very easily to understanding how much amount of the oxygens consumptions you require for the nitrification, and also how much amount of the biomass they will generated after the nitrification, and also the final effluent nitrate concentration you will get here. So you can also try to estimate uh, these three uh, chemicals consumption or productions in your biosystems.
Okay, about our next examples is talking about the methanogenesis reactions, and so the methanogenesis we will introduce in a later, that is used for anaerobic uh, microorganisms. So they are generally using like organic substance, and but they are using them in aerobically. So here the example shows that if you got like a organic like a wastewater or industrial wastewater as a representative empirical formula of CaH17O3N, because you don't have like a very standard or a very unique chemical formula that is used for industrial wastewater. So they use one empirical formula to represent the industrial wastewater chemical formula. And so if they want to use the wastewater as a couple sources, and for the anaerobic microorganisms for the methanogenesis reactions. First things they combined. Okay, they combine the RD, which is the electron donor, and using from the industrial wastewater. So that's your sources of the organics. Then they are combining another reaction RA that is used to generate the methane from the CO2. So, which is coming from the methanogenesis microorganisms, and also the cell synthesis reactions. So they synthesize the bacterial cell, and coming also from the CO2 and also the ammonia as the nitrogen sources. So the overall reactions here, they assumed the Fe would be like 0.92 and the Fs will be 0.08. So here we will know something about the methanogenesis is they spend lots of the electron to maintain their cell's energy, and just a little, very little amount of the electrons using for the cell synthesis. Okay, so if we are going to like get the overall reaction here, we can just put the Fe, Ra, and also the Fs, Rc, plus them together and minus the Rd. So the first thing here is the Fs will be 0.08 and the Fs will be 0.92. Okay, so if we combine these three reactions together to get the overall reactions we will see here. So basically, you use 0.025 molar of the wastewater, and then you will generate only 0.004 molar of the bacterial cells, and you will generate like 0.115 molar of the methane, and also produce 0.044 molar of the CO2. So if you combine the other conditions for the wastewater, for example, if you using the organic concentration that is 23,000 milligram per liter, and the wastewater flow is 150 cubic meter per day. So if you got those kind of the wastewater operation conditions, and you also got like the process is 95% efficiency to remove the organic matters, which means you only got 95% of the organic convert into like the bacterial cell and also get into the overall reaction. So finally, you can use the overall reactions here to get those numbers, such as if the molecular weight here for the wastewater is 175. Okay, so you got the equivalent weight is 0.025 times 175. Okay, then you will get like 4.375 grams per electron equivalent. So for the methane fermentation. Okay, and then you will produce again the 0.115 molar of the methane and also 0.044 molar of the CO2. So you can predict how much amount of the methane gases you will generate it. And so here is the temperature for using to calculate how much amount of the gas is volume under the 35 degrees Celsius condition. Okay, and here is the molar ratio against to the industrial wastewater. So generally you will get like 2,180 cubic meter per day methane. Okay, so you can also understanding how much amount of the methane percentage in your biogas. So we will think these two as a biogas you generate from the methanogenesis reaction. Okay, so basically this is the examples here.